Click the bell icon to get latest videos from Ekeeda.
Hello friends, welcome to finite element methods. Let us review the principal stresses and principal planes and everything about these eigenvectors and eigenvalues in the present class. Principal coordinate system of a stress tensor. Any tensor can be represented in a specific coordinate system called principal coordinate system. So we are having a stress tensor in which the stress tensor is invariant, that is the stress is invariant. The only thing that will change is the coordinates will change. That is, depending on the coordinate system, we represent the stress tensor or any tensor in that view, any tensor, whether it is a vector, whether it is a second order tensor, whether it is third order, fourth order, whether it is stiffness, compliance, whatever, all the physical entities that are dependent on the coordinate system that we represent. In the sense that only the components will change depending on the coordinate system, but they themselves won't change. So depending on that, there is some specific coordinate system called principal coordinate system, where that is very useful. That coordinate system is very useful. That stress space is very useful. Why it is useful? Let us see. Advantage 1. All the off-diagonal terms will vanish, only diagonal terms will contribute. That is, if you see the stress tensor, the diagonal terms represents the normal components and the off-diagonal terms represents the shear components. So in this space, in this particular principal space, all the stresses, all the shear stresses, all the off-diagonal terms will be 0. Only the normal components will survive. That is the nature of this coordinate system. Now, the second advantage is, since a symmetric stress tensor has 6 independent components, as we have already seen that a stress tensor will be having 6 independent components in our previous class. If you want me to show, so for this symmetric stress tensor, we are having 6 independent components, right? So what are they? Sigma xx, yy zz, xy, yz, xz. These are the 6 independent components. So now, since the shears are 0 here, what will happen here? Since the symmetric stress tensor has 6 independent components, it is difficult to imagine a 6-dimensional space. That is why in the principal coordinate system, what happens is these shears will become 0. That is, it will boil down to only 3 individual components. 3D space is something we can imagine. So that is why this stress space will allow us to imagine the stress in this 3D space. How does it look like? So where this is sigma 1, sigma 2 and sigma 3. And since sigma is symmetric, in the principal coordinate space, the stress tensor will become like this. All the off-diagonal components will become 0, only the diagonal components will survive. So this is in some particular coordinate system. The same stress tensor, I am talking about the same stress tensor. So here and here the stress tensor is same, but the coordinate systems are different. So here, for this coordinate system, we need all the components, but for this coordinate system, we need only 3 independent components, which are called the principal values, in which the nature of these principal values are like sigma 1 is greater than sigma 2 is greater than sigma 3. That is, sigma 1 is the maximum value of the stress, sigma 2 is the medium, and sigma 3 is the minimum value of the stress among these 3. These 3 are related like this. So, these principal values, what is sigma 1, sigma 2, sigma 3, are called the eigenvalues, and the directions are called the eigenvectors in the mathematical language. So we all deal with these eigenvalues and eigenvectors in our daily life. Whatever the subject we take, we deal with these eigenvalues and eigenvectors. So eigenvalues and eigenvectors are nothing but the values of that particular tensor in this principal coordinate system. So what does they do is basically, since the shears are 0 here, there won't be any rotations will happen. So only you will be having stretchings will happen only here. So based on this concept, how to obtain these principal values, by the way, how to obtain them, how to obtain the eigenvalues for a particular stress tensor. So in the principal coordinate system, one can arrive at the following relation. What is that relation? Sigma ij nj is equal to lambda times ni. So this is very important, this relation. So all of us know this relation. So what is happening here? In the principal coordinate system, one can write this stress tensor acting on some normal as some constant times acting on the same normal. So if you expand this one, if you expand this relation, that is, this is the stress tensor, this is the plane normal, this is some scalar value, this is again the plane normal, where I represents the free index and j represents the repeated index. If you want me to write this in the matrix format, then this is sigma ij, this is nj, this is lambda, and this is again same ni, again the same normal. So keeping this in mind, now if you bring all the right hand terms to the left hand side, and if you take n1, n2, n3, whatever the common terms are there, if you take them as common, then you will boil down to these three equations. Now this is a linear system of equations which is homogeneous in nature. So for this system of equations, for a solution to exist, what is the prerequisite? The determinant of this coefficient matrix must be non-zero. Must be zero. It must vanish. So the above three simultaneous equations can be solved for non-trivial solutions only if the determinant of the coefficient matrix vanishes. That means the determinant of the coefficient matrix is this: sigma 1 1 minus lambda, sigma 1 to sigma 1 3, sigma 2 1, sigma 2 2 minus lambda, sigma 2 3, sigma 3 1, sigma 3 2, sigma 3 3 minus lambda. So this is the coefficient matrix. The determinant of this coefficient matrix must vanish. The above determinant will lead to a cubic equation in terms of lambda. This will lead to the three roots of the equation, which are called the principal values or the Eigen values of the stress tensor. That is, these are the max min values. What we get is from this. So if you expand the determinant, then you will get a cubic equation which is called the characteristic equation. So that cubic equation appears like this. So it is lambda cube. Be aware of these signs. They can manage. It can be manageable. So lambda cube minus I1 lambda square minus I2 lambda minus I3 is equal to 0, where this I1, I2, I3 are called the invariants of the stress tensor. So what I meant by invariant is, if you write the same characteristic equation for the stress tensor which is in some other coordinate system instead of the principal coordinate system, then you will end up with the same characteristic equation. Because what we say is, if you want me to explain more, what I want to say is, here is a stress tensor which is in some coordinate system xyz. Here is a stress tensor which is the principal coordinate system. But both the stress tensors are same. The components are different. So for the stress tensor to be the same, the principal values must be same. That is, max min values must not change. Even the components changes, it must not change. That is, the characteristic equation must be same. So that is why for this characteristic equation to be same irrespective of the coordinate system, these coefficients must not change. These I1, I2 and I3 must not change. That is why these I1, I2, I3 are called the invariants of the stress tensor. So by the way, what are these invariants now? This I1 is called, they are like some combinations of the stress components. So for I1 is equal to, I1 is nothing but sigma 1 1 plus sigma 2 2 plus sigma 3 3. Nothing but trace sigma. So if you see the stress tensor, the summation of the diagonal components will give you the trace, that is nothing but the first invariant. Now the second invariant is summation of the minors of the diagonal components, that is the I2, the second invariant. So that can be condensed into this form: half sigma ii sigma jj minus sigma ij sigma ji, or half trace sigma whole square minus trace sigma square. This is the second invariant. While coming to the third invariant, that is nothing but the determinant of our stress tensor. That is the third invariant. Now, the above three values I1, I2, I3 are independent of the coordinate system. That is the reason why they are called the invariants. This I already mentioned. The three roots are real due to the symmetricity of the stress tensor. This is one more point we need to keep in mind. For this characteristic equation, which is a cubic in nature, we will get three roots for this equation. So the three roots will be completely real because the stress tensor is symmetric. The eigenvalues for a symmetric matrix, we know the nature of the symmetric matrix. The eigenvalues for a symmetric matrix are always real. Okay, are always real and positive. So that is why these roots are real due to the symmetricity of the stress tensor. For each eigenvalue, we will have a corresponding eigenvector which indicates the direction in which this principal value is happening. So we are having 3 principal values. So for each principal value, you will be having some particular direction. That direction is called the eigenvector. So how can you find the eigenvector? You will get the eigenvalues, go and substitute each value in the particular coordinate system, in the particular equations. Then that resulting n1, n2, n3 will give the components of that particular direction of the lambda. So the another feature is there won't be any rotation in the principal coordinate system, only stretching of the vectors will happen. These are the features of the principal coordinate system which will be very helpful for us. Thank you so much for watching this video. Stay tuned to Ekeeda, subscribe to Ekeeda.